Alright, welcome to the next tutorial in this PyTorch series of tutorials. So previously in the tutorials we had looked at uh, some basic properties of PyTorch and followed by what are the basic workflow of any PyTorch training regimen. And in the previous tutorial, we had looked at defining and training a toy model for a regression problem. Now we will take a slightly complexer problem and try to look at classification using PyTorch neural network. So let's start with defining some data that we will use for training. We are creating dummy data, and this is what the data looks like. So what we have used for creating this data is this make circles. It's a inbuilt functionality in sklearn library, and this is the syntax we are using for creating some toy data that we can use for training our classification algorithm. So it's the inputs are two-dimensional. You have two variables x1 and x2, and you have one y, a label associated with each of that sample. So it's either 1 or 0. So typical classification problem. And you have a balanced data set, like you have two classes 0 and 1, and both are equally represented. And here you are plotting the particular data that you created, and the color is making the distinction between 0 and 1. Right? The reds are one class and the blues are another class. So essentially you have to train a network that is able to distinguish between red classes versus a blue class, and you will do this using a neural network. So let's see how you would do that. So before you can define a network and get to train it, you would have to convert your data into a format that the neural network can play around with, and that is a tensor. So this is basic syntax for converting your data into tensors, right? Torch dot from numpy dot, and you are defining what is the type of that tensor. So now you have successfully converted your x and y, the training data, the whole data into tensors. Right, so this is again x1 and x2, and these are all the labels associated with data. Here we have printed the first 5 elements of that x and y. And similar to the previous example we saw in linear regressions case, you start out with splitting the data into train and test. So the split percentage that you have used is 0.2. So test data would be 20% of the training data. That is, since you started with 1000 samples, then the split now would be 800 training samples up as opposed to 200 test samples. Right, so let's get into building a neural network. These are the simple imports that you need to do: torch and NN from torch. And again, this is, you might have seen this earlier, is where we are defining a device. You might already know that neural networks train much faster on GPUs. So but it's not a guarantee that everybody has a GPU. So you should make your code as device agnostic as possible. So it should run on GPUs, as well as if you don't have a GPU, it should be able to run on CPUs and RAM. So this is where you define that variable, where you are checking whether GPUs are available, and this is the syntax to do that. Torch.CUDA is available. If it is available, you will use GPU. If it's not available, you use CPU, right? And from here on, you will use this device which will contain that information of whether GPU is available or CPU is available. Right? So this is one way to make your code device agnostic. It should run on GPU as well or CPU as well. So this is a simple model class definition, where again we are the super class we are inheriting from nn.module. In init we are defining some basic parameters of the model, and forward we are defining how should the given an input, how should it propagate through the neural network. So here we have defined two linear layers. since you get your input size is 2, you get x1 and x2. This linear layer will expand it to 5 features, and those 5 features flow into layer 2, which takes an input of 5 and gives an output of 1 feature, right? So in comes 2, layer 1 outputs 5 features, layer 2 takes 5 features and outputs 1 feature, right? And this 1 feature is what our, let's say, the model prediction would be. And in forward we are defining, let's say an x comes through, how would it propagate? First it will go through layer 1, after that the output of layer 1 will go through layer 2, right? So using that class definition, we have instantiated a model called model 0. And if you print that model, you can see that these are all the layers, these are all the weights, and the layers and their associated what are each of those layers defined in a neural network. So we had defined 2 layers, layer 1 and layer 2, and that's what get printed if you say model 0. So again, this is something that we had looked at while we are discussing how do you the theoretical aspects of training a neural network, and we had looked at you have multiple layers, and each layer might have arbitrary depth associated with each of those layer. So the same thing as we had done here, where we had defined layer 1 and then layer 2, and once the input comes, it will pass through layer 1 followed by layer 2. You can also do that by defining like this, as simple as this, where you say model 0 is equal to an end of sequential layer 1 and layer 2, and you send it to whatever device you have access to, a GPU or CPU. Now this is equivalent, this way of defining a model with 2 linear layers with the same number of features is same as defining a model using this class definition. But one assumption that this syntax makes is that all the propagation of inputs through the neural network is sequential. By sequential we mean that it comes once we have an X input features, they pass through each of those layers of the neural network sequentially, one after another, right? This is a good assumption to make when the networks are simple. It is a very simple feed forward neural networks, but this is all not the case always, right? Sometimes it's not a correct assumption to make that the input is progressing through the neural network in a sequential manner, one after another. So that's why for prototyping complexer neural networks, we would go to defining that neural network using this kind of class definition as opposed to an end dot sequential. Right. So just to check out what are the initial untrained models predictions look like, we take the models predictions and we try to just to get a sense of what are the model predictions initially without any training, right? So that we get a sense of what is the training actually doing. Right. So before we get into training, one concept we should probably cover is a kind of loss function that you would use for classification. If you remember the previous tutorial where we were doing some linear regression problem, a very simple linear regression problem, the loss that we were using was L1 loss, which is basically a mean absolute error loss, which is suitable for a linear regression. Whereas when it comes to classification, what you would have to use is something like a BC loss, binary cross entropy loss, or binary cross entropy loss with Logits. Right. Again, all of these implementation of loss functions you are taking from torch.nl. If it is a binary class, you can use BC loss with Logits or BC loss. If it is a multi-class classification where you have more than 2 classes, then you can use a cross entropy loss. So for the purpose of this tutorial, we would be going ahead with BC with Logits loss. And there is some discussion involved here as to what's the difference between these two. I would leave it to you to go through them. So now that we have some dummy data, we have defined some network. Let's define the next 2 important parameters of the training regimen: a loss function and an optimizer. Right. This is essentially the same as what we had defined in the linear regression problem, only the loss function is changing. And we are defining some function for calculating the accuracy, where it compares that the actual labels versus the model prediction labels and returns whatever the accuracy of that model predictions were. Based on our model has essentially two linear layers, and the output of the last linear layer is basically one feature, right? So if you look at those output of those model predictions, you will see that they are some random values, because also the model is not trained right now. So for you to how do you, based on this network output, how do you assign whether this particular input was either from class 0 and 1? Remember, we are doing a classification problem. At the end of the day, each x is associated with the label 0 or 1. Right? But you have defined a model which is essentially outputting some random value. It could be positive or negative, and from this you have to arrive at a class prediction, right? So how do you do that? So here we would one way to probably approach this problem is you pass this logits, whatever the model's outputs are, and put it through a sigmoid function. So sigmoid function would give you a value bounded between 0 and 1, and you can put some threshold saying that if this value is above 0.5, I'll give it class 1. If this value is below 0.5, I'll give it class 0, right? And this threshold could be again something that you would have to set manually, right? But essential concept to understand here is that model will output some logits. Those logits you will pass through a sigmoid function, and you can put some threshold on the sigmoid function and say that above that threshold is class 1 and below that threshold is class 0. You could also say that the threshold could be 0.6 or 0.4. It's not a theoretical limitation that you have to put only 0.5. You can put any number that suits your purpose, right? So now that you have converted the logits into let's say sigmoid outputs or probabilities, you can then use this syntax to convert them into class 0 or 1. And essentially what is getting printed here is whether the prediction and prediction labels are same or not. And yeah, so here the ypreds is basically a rounded up value of ypred props. So ypred props was basically output of the sigmoid function, and if you're doing rounding off, it would either make it 1 or 0. And you can also do, let's say, torch.round, and this is the whole thing that is happening. So if you unroll this ypred into what was its value, it is torch.sigmoid followed by torch.sigmoid of the model outputs, right? So this is basically a sanity check to ensure that these two are the same. The ypreds and ypred labels are the same, and they are essentially the same. And if you print the ypreds, the predictions, you can see that now they are either zeros or ones. So initially there were some random values. You made sigmoids out of them, and using some rounding off, you converted them into zeros and ones, right? So here is where we are essentially telling how to go from models output logits to model predictions in terms of classes. Right. So now let's go ahead and see how do we train this network. And you can see that this is essentially the same workflow that we have seen in the regression example. You define some number of epochs, put the model in train, do a forward pass, make some predictions. To the loss functions, you have to give y logits and y train, and based on that you can compute some accuracy as well. Now based on the loss, you will do a backward propagation, and then based on that gradient calculation, you will do a optimization step, and followed by you can do a evaluation at the end of each epoch. to tell you at that epoch what is the model performance. And you can, at every 10th epoch, you can print what is the loss, what is the accuracy, what is the test loss, what is the test accuracy. And you can see that accuracy is sort of increasing from 49 to 50, but it is plateauing out at 50. Whereas test loss and test accuracy are not uniformly decreasing. Test accuracy starts at 50, but then it keeps on decreasing till 47.5, right? So yeah, so the code above basically is telling you or trying to visualize what is a model learning, right? So model is learning this decision boundary where any point falling in this blue region is basically a blue sample. Anything in this pink or red region is a red sample. So you can see that, and this is again done for both train and test, and you can see that it's not doing a very good job at splitting the data, right? And this sort of visually tells you why these accuracies are 50 and less than 50 across train and test, right? So it is still learning some linear decision boundary, which is not good enough to classify this data. So now that you understood that model is not good enough to classify this problem, what are the ways, what are the methods that you can, what are the changes that you can do to improve the model? One is that you can add more layers, you can add more hidden layers. You can do a longer training. Let's say you do this, you keep on training for more number of epochs, and change the activation function, changing the learning rate, change the loss function, etc. Right. So let's define another model, a newer model with some modifications to it, right? So we have, so here we are defining model 1 or V1 of that particular model, and if you compare this with the definition of a previous model, you can see that we have added one more layer, right? In comes 2 features. Layer 1 outputs 10, layer 2 takes 10 features, outputs another 10 features, layer 3 takes those 10 features and outputs 1 feature. So you can, as compared to the previous model, you can see that we have added an extra layer, and also in those extra layers where previously there were only 5 out features, so we have increased that depth also. So these out features of these linear layers is also increased from 5 to 10. So you have increased the layer number of layers, and also you have increased the depth of each of those layers. So again, training this network is no different from the previous one. It is essentially the same training loop, and you can have increase the number of epochs as well, right? But the code or the workflow is essentially the same, right? So if you again you can plot those plot the model's learning and prediction boundaries, and you can see that this is still plotting a linear decision boundary and not good enough to classify the data, right? Right. So here is some code to basically verify whether the model is good enough to fit a linear data, and you can use the same network to fit a linear data, and you can see that it is good enough to fit some linear data, right? But the missing piece in this equation, where we have this kind of data to classify, the missing piece here is a non-linearity, right? Because here, no matter how many straight lines you draw, it's very hard for these, it would be terribly difficult for these straight lines to distinguish between these between these two classes, because essentially you have to draw a non-linear curve like a circle or an ellipse to distinguish these two classes, right? So that's what we would add now to our model. We would add some non-linearity to see if by introducing a non-linearity, can we achieve good classification performance in this, right? Because previously we had tried increasing the network layers and network depth. They did not help us, because inherently the data itself is non-linear, and without introducing any non-linearity, it would not be easy to fit a model for a non-linear data. So the way that we are doing here is, again, we are defining a version 2 of that model. We started with V0, we looked at V1, we are now at V2. We are defining a nonlinear function called ReLU. Nonlinear function, activation function, non-linearity, these are used synonymously in this tutorial. But the key takeaway here is that we are using activation function called ReLU, right? PyTorch has a bunch of nonlinear functions that it pre-implements, ReLU being one of them, a quite popular one and most common. So let's see what it does, and you can also take you can visually also look at the training dynamics by looking at TensorFlow Playground that we had looked at one of the previous tutorials. But following on, we use the same loss function and we use the same optimizers, but only difference between V1 and V2 now is that we are adding a nonlinearity. Also look at the forward function of this improved network or the new network, where initially what you were doing were in the V1 or V0 model, you're taking linear layers output and passing on to the next linear layer output. But what is happening here is that before you pass on layer 1's output, you apply a non-linearity, that is ReLU, right? Before you pass on layer 2's output to layer 3, you are applying a ReLU, non-linearity to the network. So now let's try to look at how is the network training. So both, you can see that both train and test, the accuracies are improving and also losses are decreasing. Right. So now let's try to look at what was the training, what does the decision boundary look like now, right? And you can see that so what we are plotting here is model 1's train sets prediction over the train set, and on the right side you have model 3 and its test set. Right. So what you can clearly see the difference between model 1 and model 3 is that it is learning a nonlinear decision boundary, and it is able to, it's doing much better job at distinguishing the two classes, red versus blue. Right. So again, this is how activation function like ReLU looks like. This is just a simple visualization to tell you what is the non-linearity that it is adding, and this is a plot of a sigmoid function. So you can essentially do the same thing with a multi-class classification as well. So far we were looking only at a binary classification problem where there were two classes, the red dot versus the blue dots. But let's say if you had more classes, more than two classes, the example that we are taking here is 4 classes, right? So you have some data which has 4 classes. You have a 2-dimensional input data, x1 and x2, and again make blobs is a function that we are borrowing from sklearn to create some dummy data, and you can see that there are 4 classes here, right? So now the problem is a bit more difficult when you compare it to the binary classification, and the network has to learn a much complexer decision boundaries to be able to distinguish this data, right? So what is changing here? You are still to start with, you are still relying on linear layers. 2 becomes 8, 8 becomes 8, and 8 outputs 4. And the loss function that you're using here is cross entropy loss. You're essentially using the same optimizer. But let's skip forward and let's see what is the model doing now. Even without using any non-linearity, just by using linear layers, you are able to achieve very good train and test accuracy, right? Let's try to look at let's try to visualize it similar to the way that we did before. This is the train and this is the test, and you can see that by these linear layers are quite good at distinguishing this data, right? So while this is multi-class classification, even by learning these linear decision boundaries or combination of these linear decision boundaries, you can train a network to distinguish between these 4 classes, and does not really require any non-linearity by design, right? So it depends on your neural network. Does it need non-linearity or linearity? Essentially depends on the distribution of your data. If it is classifiable by using linear decision boundaries, there is absolutely no need to introduce a non-linearity, right? And what follows from here on is some code on how you can compute some performance metrics like accuracy, precision, recall, F1, confusion metrics, or classification report. And yeah, that's pretty much it. So yeah, the code here is essentially doing that. It's taking the wipe-reads and the actual labels and the model predictions and computing the accuracy, and you can see that it's quite high. So just a quick recap. In this notebook, we had looked at a simple classification problem, and we had looked at the motivations behind introducing non-linearities in the network and how they allow a network to learn complex decision boundaries. And we had looked at some simple multi-class classification problem which could be solved by simple linear decision boundaries. Thank you for paying attention. Thank you for all the time that you put here. We'll see you in the next tutorial. Thanks.